All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good. Yeah, things are getting busy, I'm sure. The weather's warming up too, which is nice. Okay, so today we're switching to a new topic today. There were a couple of points I wanted to go over from the end of last lecture, just because the end of the last example was a little bit rushed. So I want to make sure I kind of go over those points today, beginning for maybe the first 10 minutes. And then we're switching to a new topic where we're going to dive more into convection. Okay. Besides maybe the first 10-15 minutes of class today, everything that we cover today is not going to be on the midterm. So we're basically starting the next kind of big unit. We're wrapping up conduction and we're starting on convection. Okay. All right, and so just a reminder, next Thursday, a week from today, is the midterm exam in this class. So make sure you guys are studying for that. Homework 3 is due this Sunday. So I think I changed the due date on Canvas, unless I dreamed it. But if it's not changed yet, just let me know. It's on Sunday. I'm probably going to post the solutions of homework 3 probably on Monday, just that you guys can help. It can help you guys study for the exam. Okay. All right. And everything about the midterm we talked about last time. Main thing is that you can prepare one sheet of notes, 8.5 by 11. Make sure you bring that to the exam, and make sure you bring your calculator as well. Okay. All right. Any questions before we begin? Okay. All right. So before we get into convection, I did want to take a minute to go back, just because the end of last lecture was a little bit rushed. Okay. So you don't have to write anything down just yet. I'm just kind of reminding you kind of what we went over last time. So last time, kind of the main thing that we went over was this example of time-dependent heat conduction. So we have this cast iron skillet that we're heating up over a flame, and simultaneously it's being cooled by convection on the top. Okay. And we went through the entire lump capacitance method. We started with the full lump capacitance equation. We canceled out the terms. We solved it via integrating factor, and we got this result right here. Okay. So the last thing I kind of barfed out my mouth kind of right before we left was just this idea of a steady state solution versus a transient solution. Okay. So I did that just because the homework had mentioned it, but I did want to go over that a bit more to kind of explain to you physically what's going on and why we even have a steady state temperature to begin with. Okay. Okay. So I left this note last time, which says that the steady state, or when steady, what we usually mean by steady state is the solution that persists when time gets very large. Okay. Okay. So when you're doing an unsteady convection problem and the problem asks you if there is a steady state part of the solution or what the steady state part you're going to examine your solution and look at all the places where time factors in, okay? So for this solution that we have here, I know there's a lot of symbols kind of going on here, but the only place that time actually shows up is in this exponent right there, right? So in that exponent, we have e raised to the minus HAS over rho VC times t, okay? Time is not present anywhere else, right? And so when you're asking yourself, or when the problem asks you, is this problem steady state, or is there any steady state part? You need to look at every portion of your solution here that contains time, and you need to see what happens when time gets large, okay? Okay, so in this case, the time here only occurs in this exponential function right here, right? So essentially, it shows up in this way, and I'm going to simplify just a bit. We have e raised to the sum constant minus a times t, right? This is very common for unsteady type problems. In fact, it's actually very common for a lot of physical systems that are governed by differential equations, okay? So this particular function right here, e to the minus at, we know this mathematically as a decaying exponential function. Right? It gets its name because it decays down to 0 at an exponential rate, right? And so if you plot it like this, we have time, we have e to the minus at, right? If you've ever seen this function, it looks something like this. So it starts at some value, well, it starts at 1 technically, and then it decays down to 0. Okay? It doesn't quite reach 0, but it pretty much gets there, right? For all practical purposes, it becomes 0, right? Okay. And so if you look at the value of this function at large values of t, right, we can see that the function basically goes down to 0, right? So if you go back to the solution that we obtained here, at large values of time, we can basically say that this term is eventually going to decay down at large values of time. And so there's going to be some solutions or some problems where that's it. And so if you have just pure convection, then usually what happens when you have pure convection is that the object and the fluid, they reach a thermal equilibrium, or in other words, they become the same temperature, right? But this problem was different. This problem, we had more than just convection. We also had the heat flux that was coming from the flame, right? And so in that case, we have kind of this balance here where eventually the amount of heat that's being gained by the flame is going to be equal to the amount of heat that's being lost by convection, right? And so in other words, we have a constant steady state temperature in this case. Okay? So eventually it's going to reach that point that you do have these two things kind of equal out. And that kind of tracks with what we kind of know intuitively as well, right? If you leave a cast iron skillet on a flame and you just forget about it for hours, don't do that. Your house might burn down. But eventually, that skillet is not going to reach, the temperature of the sun, right? There's going to be an equilibrium point where it can no longer heat up anymore. And that's exactly kind of what this represents. So, this point here represents the balance when the heat from the flame equals the heat loss from convection. Okay, so I wanted to spend a bit more time talking about that because, it's an important detail. Reaching a steady state temperature is something that is, important for these kinds of situations. So it's important to know kind of how to pick these out in the solutions, and important in terms of how to interpret them based on the math. Okay. All right. Any questions on this? Okay, good. On that same point, I did want to bring up an interesting situation, which is in the homework as well. What happens when you have an unsteady or transient heat conduction without convection? We'll just take a couple minutes really quick to kind of see what that looks like. Okay. So convection is quite unique, and in fact, we're going to spend a lot of time talking about it over the next few weeks. But convection is unique in the fact that the amount of convection that occurs depends on the difference between the object's temperature and the fluid temperature. Okay? In fact, we have our equation for this, which is Newton's law of cooling, which says that the convection heat loss is equal to H, convection coefficient, times T, which is temperature of the object, minus temperature of the fluid, T infinity. Okay. All right. So this is actually quite unique. And it's unique from this sense. It's unique in the sense that as these two get closer in temperature, right, and with unsteady heat conduction, we generally expect that to happen, right? And so in most cases, without any thermal production or any kind of specified heat flux, eventually the two things, the object and the fluid, eventually are going to reach the same temperature. Okay? And so as these two get closer, right, as these two get closer, then the rate of heat loss due to convection actually slows down significantly, right? And so in other words, with convection, you don't have a constant rate of heat loss. Right? It changes. And so, typically what happens, and we kind of discussed this, it was implied, it just we didn't say it explicitly. So initially, when you start an unsteady conduction problem with convection, initially you're going to have a huge burst of convection heat loss because the difference in temperature between the object and the fluid is very large. But then as time gets on, this will start to slow down. And so there's going to be less convection heat loss because the two temperatures are going to be equal to each other. Okay. And so let's see what happens when you don't have convection. Okay. In fact, let me write out the general lump capacitance equation again. Okay. So you have dt plus HAS over rho VC times T is equal to HAS over rho VC T infinity plus QS double prime by AQ over rho V plus thermal production Q dot over rho V. Okay. So that's our general lump capacitance equation that we start out with for most of our unsteady problems. Okay. Okay, so if you don't have convection, so without convection, so let's say that we have a situation where there's no air that's flowing at all, and so there's no convection at all, we can cancel these two terms here, okay? Okay, makes sense, right? So, another way that you can think of this is that without convection, the convection coefficient H is going to be 0, and so if H is 0, then both of those terms are just going to go away. Okay. All right, so now we have this expression dt is equal to QS double prime AQ over rho V plus Q dot over rho V. Okay. Now, what's interesting here is that typically, at least for the problems that we do, all of these terms here are constant. Okay. And so you can just simply take the integral of this. And so if you take the integral of this, we get T of T is equal to QS double prime AQ over rho V. I think I'm missing a C there. There should be a C here. Plus Q dot over rho V times T. Okay. So in other words, our temperature in these cases without convection, our temperature is just going to be a linear ramp. It's just going to ramp up, ramp up, and it's going to keep doing so indefinitely. There's a plus C here, but the C doesn't really matter. Okay. Yes.
The right side is constant, is that because the constant heat flux?
Yeah. So heat flux is, well, we assume, generally we assume the heat flux is constant. We assume that thermal production is constant. Density, volume, heat capacities are all material properties, so all of these are generally constant. Yeah. Of course, there is possibilities for the heat flux and thermal production to vary with time, but for this class, we're going to assume that they're constant. Yeah. Okay. So this is interesting, right? So, having a temperature just ramp up, again, you can kind of ask the question of what happens when when time reaches a very large number. Well, according to this equation, the temperature is just going to keep ramping up, which is not realistic for very large times. And so this equation here is valid for, I would say, for short times. I think I forgot who it was. Someone, I think it was Blake in my office on Tuesday. If you turn on your oven and you preheat it, generally the temperature in your oven is going to ramp up pretty linearly. But of course, there is a limit to how much you can ramp it up, because there's other factors that occur at that point. There probably is convection to some degree. There's radiation. The material, probably what's most likely going to happen is that your materials are probably going to melt if you ramp it up too much. But for short times, this equation is valid, but there's a limit to how much this linear ramp can be. Okay. Okay, so I think one of your homework problems has a solution like this. I think problem 5, part A and B, you're going to get a solution like this. So this is pretty common if you don't have convection. Okay. All right, any questions on this? Okay. All right, so that's all I want to say about transient conduction. So midterm 1 stuff stops here. Don't write this down. I'm just, unless you want to. All right. So like I mentioned, everything that we cover today, everything we cover on Tuesday, I'm going to test you on that stuff eventually, but that's going to be on midterm 2. Okay. Okay. So let's come back to these notes here. Okay, so we just kind of finished the first big unit of this class, which is conduction. Right? I know we brought convection into it, but we kind of dramatically simplified the kind of the phenomenon of convection, just so that we can do the calculations. So The second big unit in this class, and this is going to take us pretty much all the way up until, maybe week 13 of the semester, is we're going to be talking a lot more about convection. All right, so the title of this notes is Introduction to Convection. Which sounds strange because, we've already been introduced to convection. We've been using it. But do we really know convection? We're going to see today. Okay. Okay. So first, let's state kind of what we know about convection. So convection basically describes what happens when you have heat transfer to some moving fluid. Okay. That is a requirement for convection. And so if you don't have a moving fluid, if you don't have airflow, if you don't have water flow, then you don't have convection, you have conduction. Okay. And generally speaking, when you have convection, when you have fluid flow around your system, what that's going to do is that's going to enhance the amount of heat that gets transferred relative to just static conduction. Okay. All right. So again, intuitively, this is kind of what we know. There's a lot of examples of this happening in reality. So, like we talked about at the beginning of class, cooling electronics, you're always gonna have some kind of fan, or if you're extra, you can use your pool water, I guess, if you want. If you have a hot bowl of soup, you generally blow air over the top of it to cool it down so you don't burn your tongue. Wind chill is very classic example of convection. So, convection is all around us. And so it's not something that's foreign or not something that's, not observable. But let's talk about kind of why this happens. Okay. Okay. So convection, there's a camp of people, or some people who think that convection doesn't actually exist. Convection is just fake news. But let's kind of describe why. Okay. And in some sense, those people aren't wrong, because there's nothing magic that's happening with convection. Because convection, what we kind of perceive as convection, what we kind of understand as convection, is really just conduction with some bulk transport. Okay. Okay. So let me kind of illustrate this. And so we have a surface here. Okay. This surface is of some temperature. So we'll say it's some temperature Ts. Okay. And we have a fluid that is flowing by it. Okay. Okay, so let's say the fluid is of some different temperature, T infinity. And just for the sake of argument here, we'll say Ts is greater than T infinity. Okay. So in this case, what we expect is that there should be some heat loss from the surface, right? Because the surface is hotter than the fluid itself. Okay. Okay. So we all know this. This is something that we've seen before. In fact, we have an equation for this. And so we have Q convection is equal to H times Ts minus T infinity. I think I just wrote it down just 3 minutes ago. So this is Newton's law of cooling, right? Okay. So up until this point of the class, we've been using this formula, and we've been using it in our thermal circuits as well. And by making this kind of formula here, kind of what we're assuming is that, we are looking at kind of what I call the bulk temperatures. And so this Ts kind of represents the bulk temperature of the entire surface, and T infinity represents the bulk temperature of the entire fluid. Okay. I guess maybe another way to put it is this is kind of the average temperature difference, bulk/average. Okay. And any kind of micro effects, we've kind of neglected up until this point. Okay. But in reality, and people pointed this out in previous weeks too, that that heat that is lost from the surface doesn't just go to the abyss. It is actually going towards heating the fluid, right? So as heat is lost from the surface of this fluid actually is heating up. We've mostly ignored it up until this point, but let's talk about it a bit more. Okay. All right. In particular, the fluid that's flowing right next to the surface, though that fluid is going to feel this effect of Q convection the most, right? And so if we look at kind of a very thin layer next to the surface, right? This layer of fluid here is going to heat up the most compared to the other ones. Okay. Right. So that makes sense, right? Because the heat that's immediately lost from the surface goes to heat the fluid that's right next to it. Okay. So if there were no motion, so let's consider a case where there's no fluid motion at all, right? If there's no fluid motion, then this warm fluid next to the surface will actually start to slow down the heat loss that's coming from the surface. Okay. Because as that fluid next to the surface gets warmer, then the difference in temperature between the surface and the fluid right next to it that difference starts to shrink. And so, as that temperature difference starts to shrink, then Q convection starts to, get less and less, just exactly kind of what we talked about at the beginning of class today. Okay. And this is generally what happens when you have just pure conduction. So if you have just pure conduction, then eventually you're going to reach an equilibrium point where, there's just not enough temperature difference to sustain any kind of heat transfer. Okay. Right. So that's true. That's true in any case. Question, yes.
When you say there was no motion, are you talking about the motion of the fluid?
Yes, motion of the fluid. Yeah. So there's no fluid velocity. Questions? We'll get to that in a second, but this is just a hypothetical situation. If you have just a purely stagnant fluid, and you have heat transfer or heat loss from that. Yeah. There is motion in general, and there is the no slip boundary condition, which we will cover. But just for now, we're theoretically looking at a condition or a situation where there's just no motion at all. Yeah. Okay. So that's what would happen if theoretically there was no motion. But we do have motion, right? And what is that motion going to do? So that motion is actually going to help refresh the fluid that's next to the surface, because as this fluid heats up, right? As that fluid heats up, then the motion of the fluid is actually going to push that fluid away, and it's going to replace it with fresh, cooler fluid. Okay. And so this figure is getting kind of messy. Let's say with And so what we understand or what we kind of perceive as convection is, some people say is really nothing more than just conduction. It's just that you're always having this fresh source or fresh stream of kind of, cool fluid that's being pushed near the surface. And so, compared to a stagnant solid or a stagnant medium where, eventually those two things are going to reach equilibrium, right? In convection, it's much more difficult for it to reach equilibrium because the fluid is being constantly replaced and constantly being pushed away. Okay. And so this effect of, always pushing kind of fresh fluid and kind of maintaining this large temperature difference between the surface and the fluid, this is kind of what we perceive as convection. And that's why it always kind of provides an enhancement over pure conduction. Okay. So that's kind of physically what's happening with convection. So convection, is one way to say it is it's nothing more than just conduction, but with bulk transport to kind of help sustain this kind of temperature difference. Okay. Now, this phenomenon here, this whole thing, we're talking about things kind of almost on the molecular level of kind of transport. So this is quite complicated, and we're going to spend the next 5-6 weeks talking about it. So it's a lot of times it's simpler just to summarize it in terms of just one convection coefficient H. Okay. But that H there's a lot going on with that H. And so, we're going to talk about how that H is solved for, how we determine it, and what factors kind of go into that H. Okay. All right. Any questions on this? Okay. And of course, we talked about this example here of a hot surface and a cool fluid, but it also works in reverse too. And so you can also have a hot fluid moving past a cool solid as well. So your air fryers or convection ovens kind of work exactly in that same way, right? So if you use your toaster oven or air fryer on the air fry setting, it's usually going to cook your food faster than if you just use a pure bake, which has just stagnant air. Okay, good. All right, so let's get into some of the details of how this actually works. And to talk about that, we need to bring up a topic from fluid mechanics called boundary layers. Okay. So did you guys cover boundary layers in your fluid mechanics class? Okay, good. Okay. So boundary layers are this phenomenon that occurs when you have a kind of a moving fluid moving past a stationary solid, right? So physically what they represent, or physically what they are a thin layer of fluid right next to the surface of the solid that represents kind of a transition period or a transition region between the surface and the fluid itself. So I know the thing with boundary layers that the math and the concepts in them can be very complicated, but I always think of boundary layers as kind of regions of transition. And so in the boundary layer, you're transitioning from the conditions at the solid surface to the conditions of the free flow or the fluid far away from the surface. Okay, so let's draw a typical boundary layer. So let's say that we have a surface here. Right, so let's say that we have a fluid that is flowing past that surface. Right. And so starting at the tip of this surface, there's going to be this thin layer of fluid that's going to form that looks kind of something like this. It kind of almost looks like a sideways parabola a little bit. Okay. Okay. All right. So this fluid is coming in. So it has some velocity. So we'll call it U infinity. So U infinity here, we'll call this to be the free stream velocity of the fluid. Okay. So we're assuming that the fluid is kind of moving past at a constant velocity. Okay. And then it's going to strike this surface. And so, quite a few things are happening once it strikes the surface. So on the one hand, right? So one thing that has to occur because your surface is stationary is that the fluid next to the surface or immediately touching the surface also has to be stationary as well. So we call this the no slip boundary condition. Okay. Which basically says that the fluid, and it's really hard to see. And so it's one of those things where, the no slip condition is something that's talked about in the class. It's not really something you can see with kind of the naked eye. So if you have airflow flowing past the surface, it looks like all of the air is flowing. But if you look with the microscope right at the fluid right next to the surface, that fluid is actually still. Right? Okay. All right. So at the surface, we know that our velocity has to be 0, but we know in the free stream, the velocity has to go up to U infinity, okay? And this transition, and so, to go from 0 to U infinity, there has to be some kind of smooth transition. It can't be kind of discontinuous. And so the boundary layer is kind of where that transition takes place, okay? And so what you can do, and what's typically done, is that, we typically draw the velocity profile or the velocity kind of distribution within the boundary layer. And it usually looks something like this. All right, and so what this curve here represents a smooth transition from the no slip boundary condition to the free stream condition. Okay. So that's kind of that's kind of one of the most important parts of the boundary layers, that this transition has to be smooth, right? Now the boundary layer may be really thin, and a lot of times the boundary layer is really thin, right? So if you characterize the height of this boundary layer, right? So typically the height of the boundary layer, we give it the symbol delta. Okay. For any given system, well, the exact height depends on the system itself, but it's not uncommon for delta here to just be, maybe a few microns thick. And so this distance is very small. But there has to be a region, there has to be a place where this transition has to be smooth. Otherwise, it kind of breaks everything that we understand about fluid mechanics. Okay. So actually, let me define delta. So delta, this is the height of the boundary layer. So that's going to be significant later. And by the way, right now we're just looking at purely the fluid mechanics, but eventually we're going to go bring this back to heat transfer as well. Okay. All right. Any questions on the boundary layer here? Okay, good. Okay. So let's talk about this kind of smooth transition because I mentioned that this was kind of the main reason, right? Okay. And so kind of one of the main reasons that we have a smooth transition here has to do with the fact that viscosity exists, right? And that's true in general, not just in boundary layers, but viscosity really helps to kind of smooth these velocity distributions out. Okay. So let's kind of remind ourselves what viscosity is. Okay. So I would say kind of the intuitive definition of viscosity is kind of the tendency for fluid particles to kind of stick together to each other. Okay. So, we can all think, everyone can kind of think of examples of highly viscous fluids. And so, fluids like honey, molasses, those are fluids that we associate as being kind of very sticky because, they don't really, it's hard to kind of move them because they stick to each other and they stick to you really, really well, right? Okay. So because viscosity kind of exists, it basically causes a neighboring fluid particle to kind of be dragged along with each other. Okay. Another way to say this is that viscosity is kind of the source of something that's really important in fluids called the shear stress. Okay. So let's dive into what that really means. And so let me draw our boundary layer again. So let me draw our surface here. Okay. And let me just focus on the distribution of velocity within the boundary layer. So let's draw this here. Okay. So this distribution here represents our velocity as a function of y. Okay. So we know just from before that the velocity has to be 0 down here because of no slip. So u is equal to 0. And then up here, u is going to be the free stream velocity, u infinity. Okay. But all along the way, we kind of have almost every intermediate value of velocity going up there. Okay. Okay. All right. So what's happening here? So, you can almost kind of think of this as, on the one hand, at the very top, the free stream is kind of pulling the fluid particles along and it's kind of forcing them to have a velocity of u infinity. Okay. So let's go ahead and write that down. So say top layer. Okay. So the free stream conditions basically make it so that that top layer fluid is being pulled. It's literally, you can think of it as, the free stream is kind of grabbing those fluid particles and saying, come on, let's go move with the velocity of u infinity. Okay. Okay. But because of viscosity, right? the layer of fluid that's immediately underneath that top layer is going to be pulled along as well. Because what's happening is that the top layer is like, oh my God, we're moving with the velocity of u infinity. They're like, I don't want to go alone. So let me grab my buddy right underneath me and we'll go along as well. But the layer underneath is like, oh, I don't want to go. And so, the velocity on the second layer is slightly lower, but it still has a velocity because it's being pulled by the top layer. Okay. And you could continue this trend all the way down as well, right? And kind of the main force that's causing this kind of layer to layer adhesion, right? The fact that this information about momentum is being transferred between the different layers, that transfer or that communication is being caused by viscosity. Right? Okay. Some people call viscosity, or the way some people describe viscosity, is that it's kind of the concept of friction in fluids as well. And so, if you think of friction the same way, so if you took, a piece of sandpaper, you kind of dragged it along kind of a surface, right? That surface is going to want to be dragged along with the sandpaper because there's roughness and there's friction between the sandpaper and the surface. And so viscosity and fluid mechanics kind of forms that same relationship. Okay, so that's what's happening at the top. At the bottom, right? At the bottom, we have a no-slip boundary condition here. So that fluid there is fixed to the ground, okay? And so, while everything above this point is going to want to be pulled to the right, this no-slip boundary condition is saying, wait a minute, I'm stuck to the surface here. Let's kind of just stay still. And so this no-slip boundary condition, or this bottommost layer, is going to try to hold all the fluid back. Okay? And so even though everything above it is going to want to be pushed to the right because of the free stream, the fluid at the bottom is pulling it back because it's in contact with the surface. Okay. And so you have these are kind of the two main driving forces in the boundary layer. So on the one hand, you have fluid at the top that's saying, let's go, go, go. And then the fluid at the bottom is saying, no, let's no, let's not go. And let's stay still. Okay. And so that's kind of what creates this kind of transition region where, all the fluid in between the free stream and the no slip kind of gets caught in between. And because of viscosity, we have this kind of smooth transition where each layer is either progressively slower as you go down or progressively faster as you go above it. Okay. So that's kind of what I mean, where the boundary layer is a transition region. So you have these kind of two extreme conditions, and there has to be a smooth transition between them because of viscosity. Okay. All right. Any questions on just the concept of viscosity and the boundary layers? Okay, good. All right, one last thing about fluid mechanics before we jump back into heat transfer is let's see mathematically how this kind of shows up in the main equation for fluid mechanics, which is Navier-Stokes. Okay, don't worry, we're not going to be solving the Navier-Stokes equation. I'm not bringing this up to traumatize everyone. This is just for illustration purposes. Okay. Okay. So remember, Navier-Stokes essentially represents the conservation of momentum in a flowing fluid. Right. Technically, it's mass and momentum, but generally when people think of Navier-Stokes, they think of the momentum part. Okay. So this partial differential equation looks like the following. And I'm just going to write the 2D version. Okay. The source of many nightmares from my college days, maybe more so for my friends than me, because I actually like this stuff. Okay. So viscosity really only enters this equation in one place in the Navier-Stokes, which is this term right here. Okay. And so oftentimes, this portion of Navier-Stokes, we often call the viscous terms. Okay. Because they are the only terms that have viscosity multiplied by them. Okay. All right. So the reason I bring this up and the reason I'm kind of writing this down here is to kind of show you the mathematical form of these terms right here. Okay. Because what do you notice? All right. First of all, we notice we have this nu right here. So this nu is viscosity. It's kinematic viscosity. Okay. Bless you. Hence the name viscous terms. But more specifically in the inside here, we have second order derivatives, right? So we have a second order derivative of u, which is the velocity in terms of x, and the second order derivative of u in terms of y. And not only are they second order derivatives, they are added to each other. Question, yes.
Why it's kinematic viscosity?
That's just the name for it. So there's two viscosities. So there's dynamic viscosity, which is mu. And then kinematic is this viscosity, which is nu. But nu is nothing more than just dynamic viscosity divided by the density of the fluid. So I think it gets the name kinematic because it doesn't have any mass associated with it. So if you look at the units for kinematic viscosity, it's like meters squared per second. But dynamic viscosity does have kilograms inside its definition. So
every time I think of kinematics, I think of the linkages and back and forth.
Yeah. I think it's similar because when you talk about the kinematics of linkages, you typically don't think about the mass of those. You think of just how their lengths and velocities kind of interact. And so kinematic viscosity is kind of the same, where you don't really care about the mass or the density of the fluid. It's just yeah, it's kind of that constant of viscosity without the mass of the yeah. Okay. Second order derivatives. So all these viscous terms here are multiplied by second order derivatives. In fact, it's all the partial derivatives added to each other. So mathematically, this actually has a specific name. This mathematical form of second order partial derivatives added to each other actually shows up quite a lot in applied physics, applied mathematics. This is what's called the Laplacian. And you don't need to know that. That's not something that you need to memorize for this class. But that is something we've actually seen before in this very class, actually. Okay. And in fact, we saw it not too long ago in the 2D heat equation. Okay. And so let me kind of refresh your memory in terms of what that looks like. Okay. And so the 2D heat equation, or one form of it, can be described as the following. So we have K multiplied by partial squared T, partial X squared, plus partial squared T, partial Y squared, okay, plus Q dot is equal to 1 over alpha partial T partial T. Okay. Right. That may not be the exact form that we had in the past, but I kind of rearranged the terms a little bit to make it similar to Navier-Stokes. Okay. I basically just multiplied this entire expression by thermal conductivity K. Okay. Okay. So if you compare the 2D heat equation with the Navier-Stokes we had above, you'll see we have this exact same Laplacian kind of structure here. So we have the second order derivatives of temperature with respect to X plus the second order derivative of temperature with respect to Y, okay, added to each other. So this also is a Laplacian. Okay. Again, there's the mathematics and kind of the intuition behind the Laplacian. We can actually talk a lot about that. But that's not important here. What is important is that the fact that these two things have the same structure means that maybe temperature is going to behave very similarly to fluid velocity. Okay. Right. And there is one particular thing that I do want to highlight here, right? In particular, the aspect of temperature that may behave similarly to fluids is the fact that maybe we're also going to have a temperature boundary layer. And of course, the answer is yes. And so, I wouldn't bring that up if it was no. So, yeah. Next thing we're going to go over is the temperature boundary layer and kind of what that represents. Okay. But before we do that, let's make one more comparison here. And it's the reason why I kind of put this equation in this form. Right. So if you look at the thermal conductivity K, the thermal conductivity K is in the exact same spot as the kinematic viscosity in Navier-Stokes, right? So that kind of implies that maybe the thermal conductivity is going to play a similar role in our thermal boundary layer as the viscosity does in the velocity boundary layer, right? There's a lot of comparisons, and that's why, thermal fluids oftentimes gets kind of lumped together because the equations are very similar. Heat transfer, fluid mechanics, they're kind of almost just like, not even, they're not close enough to be siblings, but I would say maybe they're cousins that just hang out all the time. So, they're very close and behave very, very, very much the same. Okay, any questions on this before we get into the thermal boundary layer? Okay, all right, let's get into the thermal boundary layer. Okay, so let me go ahead and draw the exact same thing that we had before. Okay. So let's say that we have a surface here. Our surface is of a certain temperature, Ts, okay? And so Ts here is going to basically take the place of our no-slip boundary condition. So Ts here is going to be the condition at the surface, okay? And then let's say we have a fluid that's flowing by it. Okay. So this fluid has a velocity, but it also has a temperature, T infinity, okay? Right. And let's say that there's a difference. So let's say that, Ts here is greater than T infinity, which is kind of our typical case, right? So just like the velocity, so just like the fluid, there has to be kind of a smooth transition area where the temperature kind kind of varies from Ts to T infinity. And we call that the thermal boundary layer. So thermal boundary layer, this is the region in a fluid flow Okay, so it's going to be the region where the temperature varies smoothly from Ts to T infinity. Okay. All right, so just like the velocity, we can also draw kind of what that looks like. Here, the curve is going to look a little bit different because we're kind of reversing it here because Ts is more hotter than T infinity. Okay. So maybe look something like this. So at the surface, the temperature is Ts, and then as you go up the boundary layer, eventually the temperature is going to transition to T infinity at the very edge of the boundary layer, right? But then in between that, you kind of have this smooth transition of temperature. We have kind of a sharper temperature difference kind of near, or sharper changes near the surface, and then that change kind of slows down as you get closer to the edge of the boundary layer. Okay. So let's talk about kind of physically what's going on. So, you know, the fluid that is kind of immediately touching the surface has to match the same temperature as the surface, right? Same as the no slip. Okay. Okay. So it's the exact same in the momentum boundary layer. Okay. So fluid immediately touching the surface has to have the same condition: momentum, temperature, thermal, all the same. Right. Okay. So just like we did with the velocity boundary layer, let's kind of look at this kind of layer by layer. So let's look at the next layer immediately above the surface. So the next layer of fluid immediately above this layer is going to be heated by the layer that's underneath it. Okay. And the mechanism for heating is actually going to be conduction. Okay. And so we can write a formula for that. So we can say that QS, I'm going to do heat flux, just so that, the concept of area is kind of, a little bit hard to interpret when you go on that micro scale. So the upward heat flux of heat from the surface to the different layers of fluid is equal to minus Kf, where Kf here is the thermal conductivity of the fluid multiplied by the temperature rate. So partial T, and in this case, is going to be in the y direction, partial T, partial y. So this right here is thermal. And this QS is the upward heat flux. Okay. And so because of conduction in this case, that layer of fluid is also going to heat up. But this second layer is also being influenced by the fluid that's in the free stream as well. Okay. So this second layer of fluid is not going to heat up, maybe all the way to TS, but it's going to get close. Okay. Okay. All right, and so this phenomenon of each layer of fluid kind of successfully heating the next layer is going to continue up until you reach the free stream condition, where the temperature at that point matches the free stream temperature. Yeah.
For convection, we're just using H.
Mhm.
Convection coefficient.
Yep.
Right? So
Yep.
now we're using K then.
We're going to bring H back in a second.
Okay.
So to kind of answer your question, H is kind of it's a bulk coefficient. So it kind of not only simulates, or not only kind of takes into account just the micro, but kind of the entire fluid. So right now what we're looking at is kind of very much on the micro scale. Yeah. But this entire unit, so the next 6 weeks is how do we transfer this micro dynamics up until a bulk coefficient. Yeah. Because the convection coefficient is a lot more useful. So that's a lot easier to work with when you're talking about, heat transfer on a macro scale, which 99% of the time that's what you're talking about. Yeah.
That assumes like a closed system or an open system, right?
It can be both. So it can be both. So actually the first unit we'll be talking about is external convection, where there is kind of a free stream, but then we're also talking about internal convection as well, because that's convection inside a pipe closed system.
So if heat always transfer from, high heat to low heat, and then at that, at the layer, the actual where the surface is hot and is transferring to cold, then wouldn't the boundary layer then be affected by that? Because I'm thinking no slip means zero velocity. So then if there's a fluid that's constantly trying to go from that hot temperature to the colder temperatures, then wouldn't the no slip wouldn't that technically be eradicated? It would just kind of disappear because it's constantly trying to get away from that, so there would be a velocity. Does that make sense?
Yeah. So when we talk no slip, we're talking about just literally just one kind of molecule thick of fluid that's right next to it. So yeah, so the thermal boundary layer is the exact same, where that one molecule thick kind of layer right next to the surface is going to have the exact same temperature of the surface itself. But then that layer is going to transfer to the next layer, which is slightly cooler than the previous one, which is goes to the next layer, which is slightly cooler than that one. So, if you're talking micro scale, you're talking about very, very small differences between each subsequent layer. The same for velocity too. And then, but then in the bulk, you know, you eventually get like a big kind of temperature difference from the surface to the fluid.
Okay, so it's not as much as the molecules switching places, it's more like the energy within them.
Exactly, exactly,
It's not that, so that's what.
exactly. Yeah. Yeah, good observation.
It's kind of like on the micro scale, it's almost like conduction between molecules. Okay.
Yes, yeah,
There's no such thing as convection.
exactly. That's why some people think convection is fake news. Yeah.
So subscript S represent.
Oh, S just there, it's a heat flux from the surface.
Okay.
Yeah.
And with the model that we were looking at right now, we're assuming that T plus is greater than T, right?
Yes, yeah,
So what if it was the other way around? Would it be a negative heat flux?
it would. So in that case, it would be, well, you'd have the same formula. It's just that the direction of heat would go the opposite. And so instead of heat leaving the surface, it would be heat, the heat will be going into the surface from the fluid. Yeah. So then this profile would then be reversed. And so if it were the opposite case, you know, it would look something like, you know, if T infinity was greater, then it would look maybe something like almost like the fluids, something like that. Yeah. Yep. Okay. Good. All right, so let's connect these two kind of concepts, and so this will kind of be the last thing that we do. And so, you know, this formula right here, like I just mentioned, this kind of represents the heat transfer to the fluid kind of on a micro scale, kind of a molecule to molecule kind of interaction. Okay. But that's not the formula that we've been using, right? So the formula that we've been using for convection has been Newton's law of cooling. Right, where we say that Q convection, and I'll do the heat flux version of this. I'm just going to divide it by A is equal to H times TS minus T infinity, right? Okay. But these two ideas, so both of these representations of convection heat transfer, they have to be reconciled because they both represent the same thing, right? So this right here, this is Q convection, this is convection heat transfer kind of on a macro scale. Okay. And really kind of the center of this entire debate or the center of this entire concept is this convection coefficient H, right? And, you know, like I told you kind of in weeks prior, this coefficient right here is actually quite complex and quite mysterious. And so, you know, a lot of what we're going to do, you know, and kind of the whole issue with convection in general is how do we determine H? Okay. That's what the next 3 to 4 weeks are going to be, just solving for H. Okay. And there's a lot more to say to that. And it's going to depend really on the situation that you're in. But before we leave today, let's make a connection between this kind of macro scale kind of perception or a macro scale understanding of convection with the micro scale that we've kind of spent a whole bunch of time today. So let's set these two expressions equal to each other. Okay. And so if we, on the one hand, we have the macro scale, which is H TS minus T infinity. Okay. Ideally, you know, because they're describing the same phenomenon, this should be equal to the same as the heat transfer on the micro scale. Which is, we just found out, was minus K of the fluid times partial T partial Y. Okay. So very quickly, let's solve for H in this expression. This is not a useful expression, so we're not going to use this, but it is helpful to for us to get some intuition from it. Okay. And so if we solve for H, we get H is equal to minus KF partial t partial y divided by Ts minus T infinity. And I regret using purple because now it's not going to stand out. Use red. Okay, this is not how we're going to compute H, because it's really kind of impossible to do this. But the reason I brought this up is I want to kind of show you maybe some of the factors that go into, how we determine H, right? And so on the one hand, we can see that H is going to depend on the thermal conductivity of the fluid. Right? The other thing it depends on, which is partial T partial Y, this is a property of the boundary layer. Okay. And since we're out of time, that's all I'll say for now, but then we'll come back on Tuesday and kind of we'll explain this kind of for questions. Yes, thank you. There should be TS. All right, so thank you guys for coming today. I apologize for going over a little bit. So when we come back on Tuesday, we'll explore this a bit more. We'll talk about kind of the different interpretations of H and how we actually solve for it, and then we'll go from there. All right, so thank you guys for coming this week. If you have any questions or if you on the homework or on the exam, definitely come by office hours. And so I have office hours right now, in 15 minutes and next week as well. So hope you have a good weekend, everyone, and see you next week.
Thank you.
Or the,
Yeah. Oh, gosh, just. Oh, I have like, we have a lot going on. Yeah.
No, I would start with
I'll send you my notes.
copy it all. Do we have time?
what is the number for it?
Oh, yeah, right. It was like.
Exactly. But if you don't have time, then I would. How would I?
That was last year.
How many,
All of our.
Those are all. So, 4 as in, for problem solving.
So there's 4 previous ones, so there's 4 questions. And then 3 problem covers. And then, so you can basically expect,
Wrong.
Ignore all those.
Sounds good.
Yeah, thank you. Yeah.
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 Everything like first out.
Who did that? Yep.
First out, like, what we learned about it.
So the first one. Yeah, so when we did talk about random production, after that, the convection stuff. Yeah. Oh,
We need to figure back.
So.